Hey everyone, and welcome. Today we are heading out on a grand tour of the cosmos to really get a handle on its biggest, most beautiful structures, galaxies. We're going to figure out how to tell them apart, what their crazy shapes can tell us, and how looking up at the night sky is literally a form of time travel. All right, let's jump right in. So just take a look at this picture. What are we seeing here? At first glance, you see this beautiful, dense cluster of golden lights, but what is it really? Is this a tight-knit family of stars inside our own galaxy, or is it something on a completely different scale? Let's figure it out. Okay, so the very first step in our cosmic field guide is learning how to spot the difference between two things that can look almost identical. One of them is pretty close to home, cosmically speaking, and the other is just unimaginably far away. It all comes down to knowing the secret clues to look for. On the left, you've got a globular cluster. Think of it as a tightly packed ball of really old stars, all orbiting together inside our Milky Way. But on the right, that's a galaxy cluster, and here is where your mind just kind of breaks a little bit. In that image, almost every single point of light isn't a star. No, it's an entire galaxy with billions of its own stars. So what's the dead giveaway? How do we know for sure? Well, it's this amazing effect called gravitational lensing. The sheer mass of a galaxy cluster is so huge, it literally warps the fabric of space-time around it, acting like a giant cosmic magnifying glass. You see those weird, stretched-out, smeary arcs of light? That's the light from even more distant galaxies behind the cluster being bent and distorted. You only see that with something that has an absolutely insane amount of mass. Okay, so now that we know what to look for, let's put it to the test. What happens when you take a beast of a telescope, like the Hubble, point it at a tiny, seemingly empty black patch of sky, and just let it soak in the light for days and days? Well, you get this. And this is one of the most profound images ever captured by humanity. This right here is the Hubble Ultra Deep Field. And let me be clear, you are not looking at a field of stars. Nearly every single speck, every smudge, every swirl of light you see, that's a whole galaxy. There are thousands of them in this one tiny sliver of the sky, stretching back through space and time. It's like taking a core sample of the universe, seeing galaxies from all different eras in one single shot. It's breathtaking. So, how do we even begin to make sense of this cosmic zoo? Well, astronomers bring some order to the chaos by classifying galaxies into three main buckets, basically based on what they look like, their morphology. This is page 1 of our field guide to the cosmos. All right, so here are the two heavyweights, spiral galaxies and elliptical galaxies. Spirals, like our own Milky Way, are the bustling cities of the universe. They're full of gas and dust, so they're constantly forming new stars. That's why they have that beautiful bluish tint. It's the light from hot, young baby stars in their spiral arms. Ellipticals, on the other hand, are kind of like the quiet retirement communities. They're these reddish, football-shaped galaxies that have used up all their gas. They're mostly full of old, cool stars with not much new going on. And then you have the rebels, the third category, irregular galaxies. The name says it all, right? They don't have a nice, neat shape. They're often messy, chaotic-looking things, and that's usually because they've had a rough past, maybe colliding with another galaxy. But all that chaos can kick off a ton of new star formation. And while they might look like the odd ones out, they're actually super common. Our own cosmic neighbor, the Large Magellanic Cloud, is one. Okay, identifying galaxies is one thing, but this all leads to a really big question. How in the world do we know that a galaxy in that Hubble image is billions of light years away, and not just some tiny dim galaxy that's actually much closer? To figure that out, astronomers need a totally reliable way to measure distance across the universe. They need a cosmic yardstick. And that yardstick has a great name. It's called a standard candle. The whole idea is actually pretty simple. Imagine you have a 100-watt light bulb. You know exactly how bright that light bulb is supposed to be. So if you see one far away and it looks really dim, you can calculate precisely how far away it is. A standard candle is just a celestial object where we know its true brightness, its absolute luminosity. Now, astronomers have two main go-tos in their standard candle toolkit. First up are Cepheid variable stars. These are amazing stars that literally pulse, getting brighter and dimmer on a super regular schedule. And here's the magic trick. The speed of that pulse is directly tied to how bright the star truly is. Then, for the really long distances, we have type 1a supernovae. These are exploding stars that, incredibly, always detonate with the exact same peak brightness, making them perfect cosmic lighthouses. But, neither tool is perfect. Cepheids are great for galaxies that are relatively close by, but they're just single stars, so they're not bright enough to spot in the really, really distant universe. Type A supernovae, on the other hand, can briefly outshine their entire host galaxy, so we can see them clear across the cosmos. The only catch? They're super rare. You can't just point your telescope somewhere and expect to see one. You have to get lucky. So this ability to measure these enormous distances leads us to what is, hands down, one of the most mind-bending ideas in all of science. Because light doesn't travel instantaneously, when you look far out into space, you are also looking far back in time. This is it. This is one of the absolute cornerstones of cosmology. The light from a galaxy that's, say, 10 billion light-years away has been traveling for 10 billion years just to reach our telescopes. So we aren't seeing that galaxy as it is today. We are seeing it as it was 10 billion years ago, when the universe itself was just a toddler. And what that means is we can actually watch galaxies grow up. When we look at the most distant galaxies, we're seeing them in their youth. They're smaller, more chaotic, often irregular blobs that are cranking out stars like crazy. But when we look at galaxies nearby, we see them as they are now, mature, more organized, and a lot quieter. It's like having a photo album of the entire universe's history. This journey into the past also shows us that the early universe was a much more violent, energetic place. It was filled with these things called active galactic nuclei, or AGN for short. What that means is the supermassive black hole at the center of a galaxy is just feasting. It's gobbling up huge amounts of gas and dust, which causes the galaxy's core to blaze with unimaginable brightness. The absolute brightest of these are called quasars. And here's the critical clue. We find almost all of these super bright AGNs really far away, meaning we're seeing them in the distant past. We just don't see many nearby. And that's our proof. It tells us these massive black hole feeding frenzies were super common back when the universe was young. As galaxies got older, their central black holes settled down. They're still there, of course. They've just, finished the main course. All this talk of messy, chaotic galaxies brings up another really cool question. We see these incredible pictures of galaxies smashing into each other all the time. It looks like total cosmic carnage. So what actually happens when two galaxies, each with hundreds of billions of stars, collide? Well, the answer is probably not what you think. The stars themselves, they almost never ever collide. And the reason is that the space between stars is just vast. It's like two swarms of bees flying through each other. The individual bees are almost certain to miss. But the huge clouds of gas and dust, oh yeah, they slam into each other hard. And that collision compresses all that gas and triggers an absolutely spectacular firestorm of new star formation, completely reshaping the galaxies in the process. Which brings us to one last really important thought. We've just seen that a galaxy's shape, whether it's a spiral or an elliptical, is more like a snapshot of its current life stage, not its definitive origin. A big elliptical galaxy could have been born from two spirals merging together. So if the shape can change, what's the point of even classifying them? Well, the answer is that classification gives astronomers a framework, a shared language to see the patterns. It helps them track which galaxies are active, which are retired, and how they evolve over billions of years. It's the field guide that lets us read the incredible, ongoing story of our universe.